we start our journey through Calculus 2 with some applications of all the techniques of integration we learned from last semester's calculus. First, however, I want to kind of recap on some of those and maybe go a little bit deeper in some of the substitution and rewrite techniques that you learned from last semester. So first, what I want to work on is some of those earlier techniques, and actually this is section 8.1 in the textbook, basic integration rules. Okay, so most of these things are going to play off of the formulas that you learned earlier on in chapter 5. So I want to go through a couple examples in this video and highlight some of the differences of different integrals and how I handle kind of each of those techniques. So first things first, I want to look at two separate integrals here, 3 divided by x squared plus 1, and then the integral of 3x divided by x squared plus 1. So of course, the first thing you'll notice is that one of these integrals here has a 3x in the numerator, and of course the other just has a 3. One of those, in fact, I want you to recall the integration formula for the inverse tangent function, right? So the integral of du over a squared plus u squared is 1 over a arctan of u over a plus c, of course. So we know when we take the derivative of that 1 over a arctan function there, we get du, the derivative of u, whatever that little piece is, divided by a squared plus u squared. Okay, so we want to use that to our advantage. And we notice that the second integral isn't exactly that formula, right? We see the x on top is not the derivative of what we would take to be u in this original formula. What we would take to be u would be probably just this x, right? So what we see is 3 over x squared plus 1 dx. If I move out this 3 and kind of do a rewrite, I see 1 squared plus x squared, and I can then argue that u would be x and du would be just x. So that's why, du would be dx. And that's why I move out that 3, so I can then kind of directly apply this formula for the first integral I have there. And we recognize that this then doesn't work for the second integral, right? Because there's an extra x squared, the regular arctangent formula doesn't apply to that second integral. So I can go right ahead then and look and figure out what a is. In fact, a would be 1, u would be x. So I can go right to saying that this antiderivative is 3 over 1 arctan of x over 1, all right, where u is x, of course. So those guys match up as a direct application of that formula. However, the second integral, there's got to be something else that we can do to handle that extra x. Okay, so let's rewrite that. I've got that second integral there. So we try something else, right? This is not exactly that arctangent formula. So what I want to do is try to make u maybe this x squared. If that's the case, then du dx, the derivative of that is 2x. And with a little rewrite, I see that du is 2x dx. And I've got that extra dx right there. And in fact, there's an x in the numerator. The only issue is that extra 3. So there's a way we can handle that. Let's move the 3 out in the next line here. But first, again, this is not the inverse tangent formula. We move the 3 out, and we see x dx divided by x squared plus 1. And I've got 2x dx for du. If u is the entire denominator, then approximately du is the numerator, right? So I've got this substitution that I can do here. If u is x squared plus 1, then du is 2x dx. So what I've got then, x dx is replaced by 1/2 du, and x squared plus 1 is replaced by is replaced by u. I misspoke. Just a little bit of moving things around. That 1/2 is kind of in the way. Again, what I'm trying to do is go back to those basic antiderivative formulas. Okay, 1/2 du over u isn't exactly one of them. So I move out the 1/2 and I get 3/2 integral of du over u. Now this is one of those basic formulas. The integral of du over u is a natural log of u, right? So what this integral becomes is 3/2 natural log of u plus c. And when I put u back in there, I get an x squared plus 1 in my natural log. Okay? Of course, I can check myself very easily by taking a derivative, and I should get back to then the integrand of the original integral. Okay, so with a quick derivative, we check ourselves and we see that this antiderivative is indeed correct. So what I want to try to outline here is that we begin to kind of develop these recognition skills. Okay, you're always kind of trying to recognize whether the integral you have is one of those basic integration techniques. If it is, awesome, you can probably directly apply something. You might have to move some things around. If not, we usually use some rewrite techniques and substitution to recreate then one of those basic formulas. Let's do another example. I've got something very similar, and you'll notice that I've just added an extra exponent here in the numerator. Instead of before, I had a 3x, now I have a 3x squared. So the first thing we try is probably the same thing. If u is x squared plus 1, du is 2x dx, same as last time. But notice that that's not a 3x squared, or at least an x squared. That's not x squared. I need du to be x squared dx because that's what I have in my integral here, all right? So I'd maybe try something else. What can we do with that guy? Well, if we rewrite this quotient here, it really is just that. Notice that those powers in the numerator and denominator are the same. What I can try to do is actually compute that division. See if I can divide 3x squared by x squared plus 1. Write this and try to do my long division here. How many times does x squared go into 3x squared? Well, that's of course 3 times. And when I divide those, I end up with a remainder of minus 3. So the quotient that I have is actually 3, the quotient, minus the remainder, or plus the remainder, sorry, just a minus 3, divided by the divisor there, x squared plus 1. So I'm able to actually rewrite that quotient as 3 minus this new quotient. And of course, this seems more complicated, right? I did some long division, which is complicated. I've then rewritten one single expression into 2 expressions. But those 2 expressions that I have now, I can integrate both of those with the basic techniques that I already know. So this is one of those kind of methods that we use is rewriting. I didn't really have to substitute anything. In fact, the substitution that I originally tried didn't work. I rewrite it using some algebra, and I find that I can integrate both pieces now separately. So I rewrite my integral here. 3x squared divided by x squared plus 1 dx is exactly the same as the integral of 3 minus the quantity 3 divided by x squared plus 1. I can integrate 3 very easily. That's, of course, 3x. And I notice then the integral of that second expression is the integral we already found, right? That's that arctangent. 3x minus 3 arctangent of x over 1, or just x, plus c. Awesome. Cool. Let's do another one. Totally different here. The integral of e to the x tangent squared of e to the x dx. So this is definitely not one of those formulas that I have right away. This is not one of those known formulas. Okay, but what can we do? What can we do? I see some e to the x's in here. Those are clogging things up. I want to try to get rid of them if I can. And one of the nice things we know is that the derivative of e to the x is e to the x. So I can substitute. I can say if u is e to the x, then du should be e to the x dx. And I have all of those pieces right there for me. So if u is e to the x, du is e to the x dx, and I can make a clean substitution. My new integral will become tangent squared of u du. Now what do I do with this? A lot of the times we rewrite, we do a substitution, we can integrate right away, or at least that's the goal. We don't really land there here. We can try some different things. Let's see. What can we do? What can we do with this? I know some things about tangent. In fact, tangent is sine over cosine, so I can rewrite maybe sine squared of u over cosine squared of u. And I can try to substitute again, maybe with some of those cosine pieces or sine pieces. I know that the derivative of cosine is minus sine. Let's try that. If w, since I already have a u, I'm going to use w. If w is cosine of u, then dw, the derivative, is minus sine of u du. But I have a sine squared of u, right? This is not sine squared of u. So that doesn't exactly make a clean substitution, and it just doesn't work the way I want it to. I can't just square dw. Well, what if we try to substitute that cosine squared? If we try cosine squared, let's say w is cosine squared, or quantity cosine of u squared. The derivative of that, we require a little bit of chain rule, but again, this isn't sine squared. I get 2 cosine of u times minus sine of u. That doesn't really help me much either. So all of this substitution is kind of fruitless. Is there anything else we can do? I know that tangent squared showed up in one of those Pythagorean identities. The main one I know sine squared of theta plus cosine squared of theta is 1. If I divide each of these terms by cosine squared, I get a different identity, but that one involves tangent squared. Cool, that theta is meant to represent any argument, right? So what I can do then is replace tangent squared of u with secant squared minus 1. So I do that. I say that secant squared of u minus 1 is the same as tangent squared of u. And now I can actually integrate, right? I know the antiderivative of secant squared, and I know the antiderivative of 1. Have to pay attention here. I'm integrating 1 with respect to u. So when I do that, I got to be careful. Integral of secant squared of u is tangent squared of u. Actually, that's wrong. It should be just a tangent squared. I apologize. Or just a tangent. And when I integrate 1 with respect to u, I get a u, right? So when I then go to back substitute to replace, I get a tangent, should just be tangent, of e to the x minus e to the x. Forgive me. Okay, if we were to take a quick derivative of tangent of e to the x is secant squared e to the x. Chain rule gives us another e to the x, and we can move those e to the x's around to show that we get exactly what we started with. We'd require a trig identity, but we would eventually get back to this integrand here. Okay, so sometimes it takes a couple different techniques, a substitution, and then maybe another rewrite to get where we want to go. But again, we're always trying to get back to some of the basic formulas that we recognize. Okay, let's do a different one. Integral of x, square root of x plus 1. Okay, so one thing I want you to remember is that I can't just integrate this multiplication separately. I can't say that this is x squared and then the antiderivative of square root of x plus 1. Integration properties just don't quite work that way, right? And you can check this if you were if you were to take a derivative of what I have in red there, you would definitely not get this integrand, right? So that doesn't work. Let's get rid of that. So what I notice is this x plus 1 is under the radical, and typically when I try to substitute, it's things under radicals. Okay, so I'm going to try to take that away. I'm going to try to substitute. If u is x plus 1, du is 1 dx, or just dx. Okay, cool. I've got a dx, and I can just replace that then with u. I can also replace x plus 1 with u. Cool. So what I've got then is x times square root of u all times du. But I've got an extra x. right? And I know when I substitute, I need an entire integral in terms of one variable, right? I can't be mixing variables here, at least not yet. So what do I do? What can x be then in terms of u? Well, I see that I have a relationship between u and x up here. I can rewrite that to say that x is u minus 1. I just subtract 1 to the other side, and I'm able to then say that x is exactly u minus 1. So my integral becomes then u minus 1 in parentheses times square root of u du. Nice. You want to think about this as then all just powers of x or powers of u. I'm integrating some variable u, and all there are powers of u. So what I do is distribute. I distribute this square root of u, and what I get is u to the 3/2 minus u to the 1/2 because of those properties of exponents. And again, I've broken things apart because I can't integrate that multiplication separately, but I can do those two terms. I can go across that subtraction very easily. So to integrate u to the 3/2 are similar to x to the 3/2, or u to the 1/2, I add 1 to that exponent, right? I do my kind of reverse product rule. I add 1 to the exponent and divide by the new exponent, right? So for us, that gives me 2/5 u to the 5/2, and when I replace u, I get x plus 1 to the 5/2 minus 2/3 x plus 1 to the 3/2. Okay? We wouldn't have necessarily guessed this just by looking at this original problem, right? So things are a little bit tricky. We can still check ourselves here by taking a derivative. We don't exactly get this what we started with right away. There's a couple steps in between. We'd have to kind of factor and combine like terms in order to get back to this original integrand. Okay, so there's some jumps there to make, but indeed those techniques kind of still work. And this one is a substitution, but also kind of a little bit of a rewrite. But again, always trying to get back to those kind of basic formulas. So in general here, I want you to make sure that you review that basic integration formula sheet that's posted in Canvas, okay? Because almost everything we do is going to be trying to get back to those basic formulas. Those are things that we can integrate immediately, okay? And I want you to make sure that you're practicing some of the other worksheets. Practice more integration from the review section on Canvas as well. Okay, we're going to get into using these integration techniques fairly shortly, talking about chapter 7, where we have some applications of these integration techniques, looking at areas, and then we'll kind of come back to chapter 8 to learn some new techniques that we haven't seen before to evaluate things that we currently are unable to.